as we go through today's notes, it kind of has a different setup where we are discovering the rules and properties for sine and cosine. And when we're all done, we're just going to write the general rules, which should help us with the next 2 lessons for this week. So we already discussed what the parent functions of sine and cosine looked. If you have your task 1 with you from this week, go ahead and pull that out. Just a reminder, it looks like this, where we set up the table, talked about the terminology, and graphed the general equations. So that could be very helpful, like I said. You also will see the characteristics here. So I did graph the parent function of sine right here. I can tell it's the parent function because of the equation. It just says y equals sine of x. Also, it does have a period of 2 pi. Remember, a period is the length of the cycle, and for sine, that cycle would be the origin, max, intercept, min, intercept. Those are my 5 crucial points. Also keep in mind that these crucial points occur at 0, a fourth of the period length, half of the period length, 3/4 of the period length, and the full period length, which we said is 2 pi. The amplitude is half of the distance between the maximum and the minimum. We also talked about in the previous video using the line of symmetry and going to either the max or the min. So my line of symmetry, which is basically what cuts the graph in half, is right here along the x-axis for the parent function. So from that line to, I always go to the maximum, that's a distance of 1. So the amplitude is 1. Now we're going to compare this parent function to the graph of y equals 2 sine of x. So looking from this graph to this graph, what changed? How did the 2 impact the graph? The first thing I'm going to check is the period. So here is 1 cycle of sine, and that length of the cycle is 2 pi. So that's exactly the same, meaning the 2 out front did not impact the period length. However, it did impact the distance between the line of symmetry and the maximum or the minimum. So it impacted the amplitude, which is now 2 instead of 1. So it impacted the amplitude. When it asks why, it comes to deal with the fact that if we have a number out front, it can either stretch or compress a function. We talked about this in earlier graphs throughout Algebra 2. So I would really just focus on that when it pertains to the y. Just say it could stretch or compress when we have a number out front. Next, still keep in mind what our parent function looks like, so I'm actually going to scooch it right back up. Here's my parent function sine of x. Now, instead of the 2 being out front, we have a 2 with the x. So we're taking sine of 2x. So we want to see how the 2 impacted the graph. The first thing that I'm going to check is the period length. So the period would be 1 cycle, origin, max, x-intercept, min, x-intercept. Okay, so there is 1 cycle right there, which means the period length is just 1 pi. So how did the 2 impact the period length? Or what part of the graph did the 2 impact? The answer would be the period length. And when asked about why, the reason is that normally a full cycle has a period of 2 pi. But when we take 2x, we're doubling the rate or the frequency at which sine repeats its cycles. So you'll notice in the normal length of 2 pi, right here, we have 2 full cycles. So we've increased the frequency of the cycles. So when I ask about why, we could say that the 2 made it so that we had 2 cycles in the length of 2 pi. Next, it asks, what is the period of this graph? Assuming that it's a sine function, because it didn't tell us otherwise, we have origin, max, intercept, min, intercept. So that full period length goes from 0 to 4 pi. Given this is sine, what do you think the equation of this graph would be? Well, we have y equals, I know it's going to be sine of x. Now, over here, when we included a number on the inside of sine, it changed the period length. And we had a number on the outside, it changed the amplitude. So when I look at this equation, the amplitude is still 1. So I'm not going to have a number other than 1 in front of my sine. But because the period has changed from 2 pi, I do need to put a number in front. Now, when I put 2, we increased the frequency, and I had 2 cycles in the length of 2 pi. Now, I don't even have a full cycle by the time I get to full pi. Instead, at 2 pi, I only have half of the cycle, which means I'm going to put a 1/2 in front of the x. So a fraction, so a number that's less than 1, created a compression, or it slowed the frequency. Let's take a look at cosine. Cosine has a different pattern. This right here is the parent function. So that pattern is max x-intercept, min x-intercept, max. So basically, we're starting with a max and we're ending with a max. The full cycle has a period of 2 pi, and the amplitude in the parent function is 1, just like how sine, the period is 2 pi and the amplitude is 1. Now, we're asked to compare the parent function to this graph right here, which is the graph of y equals cosine x plus 3. So now we have a number on the outside. And I want you to think back to the graphs that we've done before with parabolas or other polynomial functions. Whenever we had a number on the outside, how would it move the graph? Well, the answer is that the number on the outside is what we had called a k value, and that would move the function up or down. So because this is plus 3, notice how it's moved the graph up 3 units. It could help to draw a picture of what the parent function would have looked like before the transformation. So if I compare the two, you can easily see how it's moved up 3 units. And when it asks why, just say it's the k value. Once again, this is a parent function, so you can either look here or here. But when I look at my new graph, this is a graph of y equals cosine x minus 3 pi. Now, when it's inside of the parentheses, we used to call that our h value. So outside is our k value, inside is our h value. When it was outside, it would move it up or down. So when it's inside, remember, we would move it left or right. Now the form is always x minus h. So we are subtracting a positive 3 pi, which means that we're going to have our parent function that looked like this. And then we're going to take each point and move it right 3 pi. Again, I'm taking each point and you can see how I'm moving it right 3 pi units. So I'm just going to say horizontal transformation, because h, and up here it was a vertical transformation because k. We also call horizontal transformations phase shifts. In case I use that terminology, it's a phase shift, but I kind of prefer horizontal transformation. That makes it easier for me to remember. Maybe I'll also make a note that this right here moved right, and if this would have been x plus 3 pi, we would have had to move left, because then we would subtract a negative value to get that x plus some number expression. This next question says, given this is cosine, what do you think the equation of this graph would be and why? Honestly, there's multiple answers for this one. It kind of depends how you see it. What I like to do is I graph a picture of my parent function. That just makes it easier for me to visualize what's happening here. So let's say I wanted to get from, I don't know, this maximum right here to this maximum right here. Some sort of transformation would have had to have taken place. So to get from this max to this max, I would have to move right, so that's a positive movement, I'd have to move right pi units, because we can see that this is 2 pi, so this is pi. And then I'd have to move down 1 unit, because I can see the scale is 1/2 since this was a -2. So if I were to write an equation, I'd have y equals, we said this was a cosine of x. Because there's a horizontal transformation, I know there has to be a number inside of the parentheses. And this number moves it left or right, so I moved right pi units. Remember, the form is x minus h whenever we've worked with it in the past. So it's going to be x minus a positive pi, giving me the expression x minus pi. And then on the outside, I can put a k value that would move it up or down. And since we moved down, I'm going to put -1 at the end. I could have also chosen to go from this point, or this maximum, to this maximum, and wrote an equation for that. It kind of just depends how you've seen it. I could have also gone from this to a maximum over here on the left side if I would extend that pattern that's going to repeat. It's up to you. Lastly, this right here, it's asking, how do we get from our parent function to this right here? Now, the only difference is that I put a negative out front. And keep in mind, whenever we had a negative in front of a function, what did we do in the past? And hopefully you remember that the answer is to flip it. So think about a parabola. If I had a parabola like this, which is opening up, if I were to put a negative a value, it would turn and then it would then open down. So when we flip it like that, that's called a reflection. So we're going to put, it's a reflection about the x-axis. And you can see that I still have an amplitude of 1. I still have a period of 2 pi. It's just now, instead of going origin max, x-intercept, min, x-intercept, it's origin min, x-intercept, max, x-intercept.